Okay, so time to get started. Here's where we were last time. We had just barely started on the idea of partial derivatives. In fact, I'm not even sure we got to the use of that term yet, but we were considering a special case of a special case. Keep in mind the directional derivative is really the primary construction we talked about last time. We considered a special case where you have a unit vector velocity. It kind of changes what you can do with it. You can interpret it in different nice ways. But it's a special case, and it's not, fully general in some sense. So this is a special case of that special case, where not only is it a unit vector velocity, but that velocity must further be a standard basis vector. And we went through a calculation last time as to what the punchline is, and the punchline is that you're taking what is really going to behave a lot like a single variable derivative. That looks just like the definition of a single variable derivative, where, in fact, there's really only one of the variables that's even changing at all. Most of the variables not changing. They're just fixed. They just stay there. Because, of course, you're just moving in the direction of a standard basis vector, that means you're moving in the direction of just that one variable. So when you take this special case directional derivative, you effectively are viewing all the variables as constants, and thus the entire function is thought of really as a kind of a single variable function. So, for example, let's look at how this plays out. In this case, this is the last example we did last time, as I recall. We've got a function here of two variables, a function of x and y. But if we're taking the partial derivative of this with respect to x, or said differently, if we're taking a directional derivative with velocity vector e1, then x is the only variable that's changing. So x is the only variable I actually treat like a variable. So we treat y as a constant. And when you're treating y as a constant, notice that it just kind of stays there if it's a factor of a function of x, and the derivative of x squared is 2x. Right? And then if it's a term by itself, its derivative is 0, because it's, again, a constant. Okay. So partial derivatives are really easy to compute. They're super easy to compute. I would, in fact, pose that partial derivatives are even easier to compute than single variable derivatives, because you get to just kind of take the function that you're taking the partial derivative of and just pretend that large tracts of it are constants. That's really nice, right? It's very convenient. Right. Okay. So a little bit of notation and definition. So here's our definition of a partial derivative. A partial derivative is a directional derivative where your velocity vector is a standard basis vector. And so I can interpret it. I could compute it as, with the definition of a directional derivative, which is right there. And then we went through the calculation on the previous page that says, punchline, that's computed like this. Namely, you're treating most of the variables as constants. So this notation is new. I don't believe we talked about this last time. Let me zoom in on that. You'll notice, importantly, that is not a D. Right? It looks kind of like a D, and that's on purpose, so that it looks kind of like a D, because this is kind of like a single variable derivative. Altogether, this notation looks kind of like the Leibniz notation for a single variable derivative. But ultimately, it isn't. Ultimately, this is what we're representing taking a partial derivative of a multivariable function, which is just, in fact, a slightly different thing. So, somebody came up with the idea of making this new symbol. It looks kind of like a D, but not really a D. Also, it might look to you kind of like the lowercase Greek letter delta. Very importantly, that is not a lowercase Greek letter delta. So it's just a different symbol. Whenever you encounter a new symbol, you got to take a few minutes to practice how to write it, so you don't inadvertently. It's really important that you don't write it as a D like that, and don't write it as a delta either, because it's not a delta. So you might want to think about, how would you go about writing this? I like to sort of do like that. So start on the inside and swirl counterclockwise. I suppose you could do that if you wanted, but I don't know. I have a mild preference for the former. Anyway, you're going to be writing that symbol a lot, so you want to think about making sure that you can write it comfortably. Yeah?
How do you pronounce the symbol?
That's a great question. I don't usually pronounce the symbol by itself, right? So this notation as a whole, you can pronounce, or you can enunciate as partial of f with respect to xi, or the partial derivative of f with respect to xi. I've even heard some people say partial f, partial xi. That's all fine. Yeah. I suppose if you really had to describe that symbol on its own, I think I would say that it's the partial symbol. Yeah. But I don't know that it has a name. I don't think it's from an alphabet. I think somebody made it up. No. Okay. Right. Another notation now to represent partial derivatives is this notation right here. Situations come up where you're taking a partial derivative of a function f, and you're taking that partial with respect to one of the input variables x. It's just that maybe there's a whole bunch of stuff going on, and if there's a lot of notation and you don't want the page to get just filled with notation, this is a little bit more compact. You just write it as a subscript. Just with the function that you're taking the partial of, give it a subscript of the variable with respect to which you're doing a partial. Surprisingly common notation. I don't like to use it unless I really feel like I am in need of compactifying my equation, because it is a little bit. It doesn't leap off the page at you as well. Okay. Of course, related to that, if the output value of the function is a variable that has a name, then you could do the same thing with that variable. Okay. Good news. If you have a vector-valued function, the partial derivatives are computed component-wise. And again, that's no surprise either, because partial derivatives are directional derivatives. Directional derivatives are defined with, and ultimately are, derivatives of parametric curves. And we proved long ago that derivatives of parametric curves are computed component-wise. So if you need to take a partial derivative, and there are the function you want to take the partial of has multiple output components, just do those derivatives one component at a time. Again, couldn't ask for a better answer on that. Okay. So, question: what does this mean? Do we get any special and convenient interpretations of partial derivatives? Well, yeah, absolutely. In fact, this being a special case, all the old interpretations we had of unit directional derivatives come along for free. So, for example, look at these two. Whoops. Partial derivatives, as unit directional derivatives, are factors that you multiply by input changes to get output changes, kind of. Again, awkward. This isn't really technically an input change, right? The magnitude of dx dt is not your input change. It's not your velocity. It's your speed. It's the magnitude of the velocity. But nevertheless, the partial derivative is what you multiply by the magnitude of the input change to get the output change. Okay. Because it's a unit directional derivative. Likewise for discrete changes down there. Okay. Of course, partial derivatives as special cases of unit directional derivatives, which themselves are special cases of directional derivatives. Partial derivatives are directional derivatives. So these are kind of come along for free from interpretations 1 and 2. But that partial derivative as a directional derivative is the rate of change of the output, assuming that the rate of change of the input is that given unit vector, EI. Okay. So, the last one I want to talk about goes back to unit directional derivatives, and that is, keep in mind, unit directional derivatives gives you slopes of tangent lines to the curves that are cross sections of the graph of a function. Right? So said differently, they're slopes. Precise about what they're slopes of, though. This interpretation, of course, only makes sense if you were talking about a partial derivative of a real valued function. It's got to be real valued so that the graph is actually the right kind of object here. Okay, so let's see some examples. So we're going to be looking at this function. Specifically, we're going to be looking at the graph of that function. And on that graph, I want to talk about the cross-section curve in the x direction. So here's the graph. The graph is some surface like this. And there's the x direction, there's the y direction. And looking at a particular point, 2, 1, so I'm at some point in the domain. I'm going to be moving in the x direction. We'll look at the vertical cross-section in the x direction. And that cross-section of my surface will be a curve of some sort. And I want to know what's the slope of that curve. Okay, well, the language here kind of gives everything away. We're looking at a slope of a tangent line to the cross-section of the graph of a function that is a unit directional derivative. All right. Which unit directional derivative? Well, it's the unit directional derivative in the direction that points in the x direction. Well, conveniently, the unit vector that points in the x direction is exactly E1. Right? So what we're looking for here is a unit directional derivative where our direction vector is E1, namely a partial derivative. Does that make sense to everybody? Okay. And that is great news, because look how easy it is to compute the partial derivative. It was a little worrisome, again, if you look at this function and you see, wow, there's an exponential, and oh gosh, there's a composition. Sort of a double composition, because it's y squared, and you're taking sine of that, and then you're exponentiating that. And so you have these glimpses in your mind of chain rule nightmares, right, of having to write a whole bunch of stuff down. But key point, we're taking a partial with respect to x. That means that x is our only variable, and all of this y nonsense we treat as a constant, because for the purposes of an x partial, it is a constant. So the derivative is really easy. And plug in the point in question, and there's your answer. Everybody happy? Okay. So next example. So suppose we have a bird flying through the air. And the bird, at a particular moment, is at that point and moving with this velocity. Right. Okay, now I'm keeping track of a certain function. This is the humidity function. Humidity is given by that expression. And I want to know how fast is this function changing. So now our bird is flying around in the domain of this function. I want to know how fast the output of the function is changing. And this is how fast is the humidity changing, presumably per unit time, right? So it seems to be the indication. So directional derivative, what I want to compute. Right? So specifically, I want to know the directional derivative. This is the function that I want to compute the directional derivative of. This is the point at which I want to compute its directional derivative. That's where we happen to be. It's where the bird is at that moment. And the bird's velocity, so the velocity I'll use in this directional derivative calculation is that vector right there. And now it's not a unit vector, right? But anyway, that's my vector. Conveniently, though, I can note that there's a very handy scalar to think in terms of factoring out. That scalar being this 5 here, I might want to factor that out of the vector. And likewise, you'll notice that puts it there. And so ultimately, what I want to compute then is this directional derivative. That's what it's sort of left over. That is not just a directional derivative, that's a unit directional derivative, because that's a unit vector. But even better than that, it's not just a unit vector, it's a standard basis vector. which means that the directional derivative can be computed with a partial derivative. All right. So all that being observed, I just want to compute the y partial of that thing, and well, there's you got to remember your single variable calculus derivative rules. Don't forget to use the chain rule. And here's your final answer. Everybody see how it works? Here's a different point of view on the same problem. I could have observed early on that I'm moving in the direction of a standard basis vector with speed 5. And one of my interpretations back here is that the partial derivative is what I multiply by my speed to get the rate of change of the output value of the function. Right? Now, in the example that I just showed you, I sort of walked you through observing the question as a plain directional derivative, and then sort of in some sense re-derived this result. But you could just go straight from interpretation 1 here. It's the same answer. All right. Okay, so that's partial derivatives. I want to talk about second partial derivatives now. Hopefully this isn't that big of a surprise that there are second partials. I mean, obviously there were second derivatives when you're doing single variable derivatives. Partial derivatives are a lot like single variable derivatives. Note, if you have a real valued function of several variables, when you take its partial derivative, and you still have a real valued function of several variables. And so you could ask, what might it mean to take a partial derivative of that? So here's an example where I explicitly do some. There's a function, x partial, y partial. Notice the original function, real valued function of 2 variables, the partial derivatives are both real valued functions of 2 variables. All right, so we could talk about, for example, this y partial here. I could ask, what is the x partial of that y partial? Or I could ask, what is the y partial of that y partial? And the rules are the same. The way I take, given this function, the way I take the x partial of it is I treat y like a constant. I take the derivative of, interpreting x as the only actual variable. And so I get the 3x squared has derivative of 6x, and then the y squared stays along for the ride. Right? So it's the same process. It's just that I'm taking a partial of a partial. Everybody okay? A notational observation, this notation here sometimes gets, here I pointed at the wrong one, sorry. This notation here sometimes gets compacted and written like that. Very common notation, you'll see that all the time. Likewise for the others. Also, these might be written with the shorthand notation. So this, we started with a function f, we took the x partial of it, and then of that x partial we took the y partial. So this is that sort of compact notation. You'll see that written sometimes as well. Okay. All right, well, yeah, but what does it mean? I mean, what is it? What do I do with it? What does it look like? How do I visualize a second partial? So I'm going to talk about that a little bit. I'm going to start by talking about this second partial with respect to y. I have written here. Let's try to make sense out of what that looks like. Let me walk you through. I'm going to give you 2 different points of view on this. The easiest point of view is to say that, well, what this says is I've got some function f. I want to take the y partial of it, and then I want to take the y partial of that. Okay, fine. So I'm going to take this function f. In doing that first y partial, I'm going to treat x like a constant. Now, then I take the derivative with respect to y, fine. And then when I get over to the next y partial, I'm going to continue to treat x like a constant. And take another y partial. So said differently, I'm going to treat x as a constant and take two y derivatives in succession. And we already have an intuition for what that means for both of those steps. Treating x as a constant means I'm going to look at a cross-section perpendicular to the x-axis. That's treating x as a constant. And then taking two derivatives with respect to y, well, that's just the good old single variable second derivative, and that means I'm going to be, in some sense, measuring the concavity of that cross-section to this surface. That make sense? So, good news, second partials, this particular second partial anyway, just like single variable second derivatives, is kind of a measure of concavity. But specifically, it's a measure of concavity just of that cross-section that you might call in the y direction. It's perpendicular to the x-axis, which we're treating as constant, and therefore it's in some sense in the y direction. Okay, so that's one point of view on this. Now let me give you a different point of view on how to think about what just happened, what this second partial is. I'm going to look at these two different partials. Oops, I got a y partial. And then I'm taking a y partial of that y partial. I could instead interpret the first y partials as slopes of tangent lines to the cross section. So I could think about these various tangent lines there to that cross section curve. And then I could think of the second y partial as asking what is the rate of change as I move in the y direction. Oh, whoops, I forgot to change the color. What's the rate of change as I move in the y direction of those slopes? Right? I mean, this is really just kind of a repeat of how we interpret concavity from single variable second derivatives. But nevertheless, I can interpret the outside derivative as representing a rate of change and the inside derivative as representing a slope. So we're actually going to need that point of view when I try to make sense out of the mixed partials. So let's look at this expression here. That's not a y partial of a y partial. It's not an x partial of an x partial. This is a y partial of the x partial of the function. Now, computationally, that's just, you can write this stuff down. You can compute what that is. But what does it look like? Geometrically, how do I visualize it? And here, again, I'm going to take this point of view. I'm going to take this rate of change of a slope point of view. So importantly, here the slopes are slopes in the x direction. But I want to know how those slopes in the x direction are changing as I move in the y direction. Right, so it's a harder picture to draw. Here's my attempt to draw this picture. You'll notice I didn't draw the surface because that makes the picture harder to see. It makes the picture sort of confused. But let's do these one at a time. These x partials that I'm keeping track of are slopes in the x direction. So here, for example, that's a slope. Right, that's my attempt to draw a tangent line to a curve that's pointing in the x direction. As we move in the x direction, there's sort of a tangent line. What we want to know here is, as we move in the y direction, how do those slopes change? So I want to know, as I move that way, how do these x slopes change? So you really have to think three-dimensionally now, right? So I'm going to do a little hand wavy demonstration here. So my finger here now represents a slope to a cross section pointing in the x direction. There's your x direction. There's a slope in the x direction. And now as I move in the y direction, that's this other way, I'm going to try to represent what this picture shows, which is my x direction slopes changing as I move in the y direction. So I'm going to drag my hand this way, and as I do so, the slope changes. Right? Everybody kind of see what I'm talking about? So you sort of visualize, what this looks like, and I like to think of this as kind of a twist. It's like I wish I had a sheet of rubber of some sort, but imagine you have a sheet of rubber and you kind of do this to it. Right? It's not really the way we think. It's not concavity in the sense that we normally think of it. It's sort of an opposing concavity, really. Right? It's like it's going to be concave down that way, but concave up this way. It makes a kind of a Pringle. Right? Saddle point kind of a deal. Anyway, it's a sort of a twisting of the surface, and it's a weird thing. You'll notice that it's not something that can be thought of exclusively in a single cross-section. This is not something that's happening just in that plane, or just in that plane. It's really a sort of a three-dimensional feature of the curvature of the surface. So that's what these mixed partials represent. How we doing? Everybody happy? So I'm going to appeal to your geometric intuition about something. What if I were to draw, looking at this same picture here, I'll zoom in a notch. What if I were to draw, instead of, now what I have here is a representation of a y partial of an x partial. What if I were to do it the other way? What if I were to ask, what's the x partial of the y partial? So I'd be wanting to look at slopes in the y direction and wanting to know how those slopes change as I move in the x direction. So I hope this is going to work decently well. It's going to be messy. But here are slopes in the y direction. And there are those slopes changing as I move in the x direction. And interestingly, now you'll notice I tried to do this in some sense on the same surface that I was looking at here. It also represents kind of a twist of the surface. In some sense, let's see here. Okay, so this is the kind of twist that we are measuring here. And this is the kind of twist we had been measuring. And do you notice that these are kind of the same? Right? In other words, in both cases, opposite corners are going up and other opposite corners are going down. And whether I hold it like this and do that, or whether I hold it like this and do that, it's the same movement on the four corners. So geometrically, you sort of expect that when you have this sort of a mixed partial twisting, you should effectively be creating the other mixed partial twisting as well. And this is represented algebraically in the wonderful little result down here, that under certain conditions, that we'll talk about in a second, those mixed partials are the same. And most of the time this is true. So I have this phrase as the xi partial and the xj partial. But whether you're taking the xi partial of the xj partial or the xj partial of the xi partial, you're just kind of two different points of view on what's ultimately the same kind of pringling of your surface. So not terribly surprising that those mixed partials are the same. Okay. So again, now there is, just as a formal matter, there's a condition. You do need the function to be sufficiently regular for this to actually be true. You need specifically for those second partials to all be continuous. Otherwise, there are counterexamples. There are weird, anomalous little oddball counterexamples. And in order to ensure that that doesn't happen, we have to require the second partials to be continuous. But most of the time, you expect the second partials to be equal. Okay. Questions? So now let me make a quick observation about the order of topics in this book. I started derivatives, you'll recall, with derivatives of parametric curves. And that's because we use derivatives of parametric curves in what I would hope that what I always want to be your sort of basic foundational point of view on derivatives, which is directional derivatives, namely input changes and output changes. And I just needed the output changes ended up being the derivative of parametric curves, so we had to do parametric curves first. But in some sense, the most fundamental point of view that I've given you about multivariable derivatives is directional derivatives. So it's a relationship between input changes and output changes. And that's the way you should think about derivatives. But partial derivatives are really easy to write down and really easy to compute. So most textbooks on multivariable calculus actually start with partial derivatives. Furthermore, lots of more sophisticated objects that we're going to talk about later on in this course. So in Chapter 6, we'll be talking about something called divergence. It's a very important geometric idea and physical idea. Very easy to write it in terms of partial derivatives because partial derivatives are super easy to compute. And it's just really, really natural to write it this way. There are other ways to write it, but this is really, really handy because of how easy these partial derivatives are to compute. Anyway, I just wanted you guys to be aware of this fact that, again, most multivariable calculus starts off with partial derivatives. I feel that to make sure that you have the right picture in your mind and that you have the right sort of perspective of thinking about derivatives as relationships between input changes and output changes, that it's better to wait and do it later. View it as it is, as a special case of this more general construction. Get that more general construction into your heads first, and then the computational convenience of partial derivatives will always be there, and so we can do it later as we have. Okay, so point of view. You'll notice in the exercises here I have you doing some computations of these more sophisticated objects. I'm going to have you do some computations with divergence because you can, because it's just partial derivatives, and you know how to do partial derivatives now. Likewise, there's a also sophisticated object called curl, and it's computed with partial derivatives. And so you can do some curl computations now. I will talk later about what divergence and curl actually mean and what they look like physically and how they relate to the physical world. It's very important stuff. For the moment, I want you to do some computations with them. And there's various other such examples in here. Lots of stuff in physics is done with partial derivatives because you can very conveniently write these various expressions. So the Laplacian operator gets used in physics a lot. This, what they call the three-dimensional heat operator. This is a mathematical object that can be used to study how heat flows through some sort of a medium. So I don't know if you ever really thought about this, but if you have obviously if you have two pennies, right, and one of them is hot and one of them is cold, and you put them together, then heat sort of flows from the hot one to the cold one. Some sense, right? So the temperature of the hot one goes down, the temperature of the cold one goes up. But how does the heat flow? Well, you've all seen a simple version of this, and that's Newton's law of cooling, right? And that's this very simple sort of special case. What if you have a three-dimensional, let's say, block of metal, and somebody lights a lighter underneath one of the corners? So it's not just it was on one side, heat going in just one direction. Now there's heat flowing that way and kind of into the middle of it and also kind of up. How does the heat overall kind of flow through and eventually fill up the entire cube? Where does the temperature, not only as a function of position, but as a function of time? That can be studied with this three-dimensional heat operator, which you'll notice is made up out of partial derivatives. Various other examples I'll let you guys read through here. Okay, so moving on. Do 4.6 now. 4.6 has a lot of ideas in it. It's more than I'm going to do in this course, so I'm going to skip parts of it. Some of the calculations I'll let you guys read through on your own if you're interested. Some of them are not even necessary. I'll try to point those out. Let me start by saying it's tempting to spike the football at this point. Look what we've got. We have a constructive definition. That's how you compute directional derivatives. And this works no matter which direction you're going in the domain. This really feels like we've got a fully general notion of what it means to take a derivative of a multivariable function, because we can go in any direction with it. Right? Well, it turns out that this isn't the whole story. It turns out that there's some amazing facts that happen. There's some relationships, unexpected relationships between these various different directional derivatives that at the moment we have not glimpsed. We have not seen the full story on these directional derivatives. And there's some other points of view on differentiation that we haven't had a chance to talk about either. So I'm going to talk about these a little bit now. I'm going to start with an example. So here's a polynomial function of two variables. And I'm going to give you a point and a velocity vector, and let's compute the directional derivative. Now, you might be thinking to yourself, don't we already know how to do this? Isn't this from 3 sections back? And it kind of is. But interestingly, what you'll notice is I didn't really quite give you the velocity vector. I gave you an actual point, 1, 2. I gave you an actual function to take the directional derivative of, but I didn't. All I told you about the velocity vector is that, I'm going to say the coordinates are v1 and v2. I'm going to leave these as variables. So what we're computing here, then, is a directional derivative thought of as a function of velocity. Right? So P is given. A is given. And I want to know how does this result depend on what the velocity vector is. So we're leaving it as a variable, and let's just see how it turns out. Now these are details, and let you guys read the details. And I think it'd be a good exercise to read through those details, see how this all. Make sure you can follow through, and you might even try to do this one on your own. Right? We have all the tools for this. And here's what the punchline ends up being. That is how our directional derivative is a function of that velocity vector. And something kind of interesting happens. You'll notice that it's a linear transformation. It's a pretty simple formula, in other words. It's just 2v1 plus 5v2. Flip back to chapter 3. Remind yourself what the definition of a linear transformation is. This is a linear transformation of v. And you might think, okay, well, it's not that surprising. Look at the polynomial. The polynomial is only a quadratic. There'd be a nice exercise for you. Add in like a cubic term in here. Go through the same calculation to compute directional derivative as a function of a variable velocity vector. What you'll find is still a linear transformation. So this is true for all polynomials. Now I go through a calculation here. You might want to take a look at this, but don't worry about the details. There's a lot of gory details in here. This is a general polynomial. It's going to have lots of different terms, lots of different degrees of the various terms. And I go through and I compute the directional derivative here. Lots of details. And the punchline is linear transformation. In other words, it's just a linear combination of those velocity vector coordinates. Very surprising fact. So what we've actually observed here, we've stumbled across an important fact, an important feature that a lot of functions have, surprisingly large number of functions have, and this is what I like to call directional linearity. Directional linearity says that the directional derivatives are computed with a linear transformation on the velocity vector. Given a function, once you've decided on a function, given a point from which you are doing these calculations, viewing the directional derivative only as a function of velocity, computed with a linear transformation. You'd be surprised how many functions this works for. Pick a random weird function, e to the x plus y cubed minus sine z, something weird like that, right? And go through the same game. Fix a point, leave velocity as a variable, go through, compute the directional derivatives, and yeah, weirdly, sure enough, it turns out it's a linear transformation. Okay. All right, so the theorem that I just kind of skipped over says this, and then I restate it in this language. For polynomials, you can compute the directional derivatives with a linear transformation, and then I define this term directional linearity, and then I restate the theorem. All polynomials have this feature of directional linearity, so we call them directional linear. Okay, really kind of surprising fact. Okay. Turns out there's a little bit more that you can say about most functions, and it's called differentiability. One of the awkward things about a multivariable calculus course is that it's actually pretty hard to give a really good motivation and intuition for what differentiability is. I'm not going to do it in this lecture. I'm going to give you, I'm going to write down the definition, and I'm going to make a very loose interpretation of it, and that's really all I'm going to do. So specifically, here's the definition of differentiability. This is what it means for a function to be differentiable. Roughly speaking, it means that there is a linear transformation t that makes good approximations of the function. And very loosely, the idea there is then that if you have an input change, and if you compute the corresponding color choice output change, turns out that this is a way of getting a handle on what it might mean for a linear transformation, being able to, by computing t of x minus a, do a good job of approximating f of x minus f of a. So this linear transformation using a change in the inputs to approximate the change in the outputs. So the details why you divide by magnitude of x minus a, it's a 15-minute digression, and we're not going to do that in this course. Okay. But roughly speaking, again, what this definition means is that there is a linear transformation that does a good approximation of the function. So the key takeaway from this, the important thing I want you all to note, is that this is defined with a multivariable limit. And you might recall, when we were talking about multivariable limits, we came across some really counterintuitive, surprising facts about multivariable limits. Right? You remember this one where you approach along every possible different straight line, and no matter which straight line you approach, you always get the same answer, and yet weirdly, if you approach along a spiral, you get a different answer. And so multivariable limits, punchline, really cannot be well studied by straight line approaches. Even if all of the straight line approaches are doing something nice and seemingly the same, not good enough. It's just not. Multivariable functions are more complicated than that, right? So we saw that with multivariable limits and these, approaching along spirals and approaching along quadratics and cubics and weird curves. Okay. It's the same with differentiability. This differentiability that I'm defining here is defined with a multivariable limit, is just a more substantial statement than any statement that can be made by looking simply along straight lines. And if you think about what a directional derivative is, I mean, if the word directional gives it away, you're looking at what the function's doing in a single direction. This is a derivative version of approaching along a straight line. You know, and when you're computing a directional derivative, you're just looking, you have blinders. You're not seeing any of this other stuff. You're only looking along that one straight line. So even if altogether they, in some sense, dovetail and it looks like everything's nice, the point is you've only looked along straight lines. And it just doesn't tell the whole story. So there's some deep and sophisticated facts about differentiability, and ultimately, this differentiability is a stronger condition. Even not only is it a stronger condition than your mere ability to compute directional derivatives, but it's even stronger than directional linearity. It's weird, but it's true. Yeah.
So basically, by looking along every line possible, you find a straight line that can approximate.
Yeah, that's right. I mean, you're doing one at a time. Yeah, you're computing along. If you're looking just at directional derivatives, then one at a time you're looking just along straight lines, and it just doesn't tell the whole story. Yeah, so there's some weird functions where all the directional derivatives exist. Might even be directional linear. Might be perfectly nice seeming, just like this. I mean, this seems pretty nice, right? Not only do you have directional derivatives, but they all behave. And yet there could be something very nasty and bad about this function that we just didn't notice because we weren't taking a sufficiently sophisticated point of view. We're doing one straight line at a time. So again, we can't really quite fit it into Math 212 to talk about the further details on that. So I will tell you, though, two things. So first of all, differentiability is a stronger condition than directional linearity. So if the function is differentiable, then it's definitely directional linear. That means that all the directional derivatives exist. It means that those directional derivatives fit together in this really nice linear fashion like we observed with polynomials in our first example. So differentiability is a strong condition. Second thing I want to tell you is that differentiability is actually important. I mean, even though directional linearity, in some sense, tells us a lot. Sometimes we need more. We need to know that a function is not just directional linear, but differentiable in the multivariable sense for certain theorems to be true. And again, there's a sophisticated discussion there that I can't really go into. Okay, so if this is the case, if a function is differentiable, that is, if it is well approximated by a linear transformation. If there is a linear transformation, in other words, that does this good job of relating input changes to output changes, that linear transformation, we give it a name. We call that the derivative transformation of the function. So it's a linear transformation. It is the linear transformation that makes this work. And it's, yeah. Right. So it's called the derivative transformation of the function. Importantly, as the linear transformation that makes this work, it's the linear approximation. It's the linear transformation that relates input changes to output changes, and therefore it is the linear transformation that computes directional derivatives. So not only is every differentiable function directional linear, but the derivative transformation is the linear transformation that realizes that linear relationship between your directional derivatives. So it's not terribly surprising if you think about it. I mean, just from a notational standpoint, and this is a silly observation, but let me zoom in here. You look at this equation, and you observe that there's a D, an F, an A, and a V on both sides of the equation. Right? It kind of just looks like you're shuffling notation around. Now, importantly, that's not what's happening. This says, I'm going to look at this function f, starting from the point A, and one direction at a time, look along certain direction vectors v. So this is a relatively simple object. One direction at a time. This is ultimately kind of a single variable derivative applied in a multivariable setting. This is a truly multivariable derivative. This says, look. We're at the point A. We've got a function f at the point A. Keep your vector for the moment. I don't want to talk about vectors yet. I want to know, is there a multivariable sense in which I can understand how this function is changing near the point A? Can I understand all of those changes all simultaneously in the form of this one linear transformation? And then, if yes, if so, then great, fantastic, give me one vector at a time and I can pop them into this linear transformation. And yes, they'll always give you the same as if you took this more naive single variable approach. But this is defined in a much more sophisticated and powerful way. Okay. All right, so some nice rephrases of this. Let's look, and I'm going to zoom in on this too. This is also important. Let's look at these. I can zoom in one more notch. There we go. Look at these facts. The derivative transformation, that linear transformation, we get to really fully, finally recover a feature that we expressed as one of our goals way back in single variable calculus. Remember, the very first thing we said about derivatives in this chapter was we re-examined what is a single variable derivative. We decided that a single variable derivative is a relationship between input changes and output changes. And I would like to have some way to do the same kind of thing in multivariable. In single variable, a derivative is something you do to an input change to get an output change. We wanted, fingers crossed, a thing that I could do to an input change in a multivariable context to get the output change in a multivariable context. And we now have that. The derivative transformation is what you do to input changes, be they discrete changes or rates of change, to get output changes, be they discrete changes or rates of change. Ultimately, then, the derivative transformation is the most general and powerful way to think about derivatives of a multivariable function. This linear transformation is the relationship between these input vectors and those output vectors. You remember a long time ago when we wrote this down? We wrote down the following little calculation in single variable calculus. We write down f prime as limit delta f over delta x, and so we thought, well, why don't we do the same thing in the multivariable context? Why wouldn't we just take a limit of delta f over, that's a vector now, over delta x, and that's a vector now. And then we kind of chuckled at our silliness, because you can't divide a vector by a vector. That doesn't make any sense. Right? But this was our sort of naive first thought at how I might take a derivative of a multivariable function. We just can't divide vectors. But you can, though, think of a derivative not as a fraction between two vectors, but as a factor relating two vectors. So the derivative transformation is how we realize that goal. Okay. All right. I'm going to move on. Okay. So these are those same statements, just said in words. Right. So the first example here is just an observation. We've already kind of realized this in a previous example. We were looking at that point, and we tried to compute the directional derivatives as a function of the velocity vector, and we went through, and there were some details I left for you guys, but here was the punchline. There's a linear transformation that represents all these directional derivatives. So all at once, this linear transformation computes all of my directional derivatives. Well, then that is my derivative transformation. The derivative transformation is that function. Said differently, here's the matrix that represents that linear transformation. So thinking back to chapter 3, how we represent linear transformations with matrices, this is the matrix that does it. Okay. All right. One last big idea I need to talk about is continuous differentiability. This is another notion, another feature that a function might have. It's actually really easy to define. Continuously differentiable function is just a function where the partial derivatives exist and are continuous. That's it. It's a disappointingly simple definition. When I gave you all a whole speech about how it's really hard to talk about differentiability. Differentiability is this sophisticated, kind of deep, multivariable point of view on how we might talk about how to approximate changes of function. It's a really pretty significant conversation. Not continuous differentiability. That's easy. Continuous differentiability, partial derivatives exist and are continuous. End of story. And the wonderful thing, and this is a powerful fact that you guys are going to use a lot, is that if a function is continuously differentiable, then it is also differentiable. In other words, this easier to check condition, this downright easy to check condition, always gives you, as a result, the much more sophisticated and deep sense of differentiability. So we're going to be doing this quite a bit. If you need to know that a function is differentiable in this course, pretty much the only, I'm going to be able to state certain theorems, certain categories of functions are just known to be differentiable. But other than that, if I need you to sort of prove it, check that a function is continuously differentiable. If you know it's continuously differentiable, then it's differentiable. That's how you do that. So, for example, how would I check if this function here is differentiable everywhere? Well, gosh, it's are we going to write down a multivariable limit? I mean, there's a multivariable limit that defines differentiability. Am I going to try to compute that multivariable limit? Find that linear transformation that does what it's supposed to do and makes this multivariable limit go to 0? No, I'm not going to do that. That's hard. It sounds like work. Right? What I'm going to do in this case is I'm going to take this function. I'm going to write down all of the partial derivatives. Notice that there are 2 output variables. Each I can take the partial with respect to each of 2 input variables. That gives me 4 partial derivatives. I'm going to casually glance at all 4 of these partial derivatives, observe that they are all continuous, declare continuous differentiability, and therefore differentiability. Very easy to do. Does everybody see how this works? Okay. Right, so we've talked actually about a lot of different kinds of differentiability. I summarized them all with this little hierarchy, I like to call it. So we just talked about continuous differentiability. And that's what continuous differentiability is. We talked about differentiability, but I didn't really expand on the details, but I said very, very loosely that a function is differentiable if you can make good linear approximations of it with some linear transformation. I didn't go into the details. We did talk significantly about directional linearity, namely a function's directional linear if directional derivatives can be computed with a linear transformation, like that polynomial that we saw at the start of this section. So these are all different notions. Interestingly, though, they nest. They stack one on top of another. Every continuously differentiable function is differentiable. We just talked about that. Every differentiable function is directional linear. We talked about that a few minutes ago. And then the hierarchy kind of continues. Every directional linear function is what I'm going to call directionally differentiable. In other words, the directional derivatives all exist. That's a silly observation. If they all exist and are linear, then they all exist. Okay? Not a deep observation. And then lastly, if it's directionally differentiable, then it's partial differentiable. So if all the directional derivatives exist, including the partial derivatives, well then, yes, the partial derivatives exist as well. It's, again, a free. So we have 5 different kinds of conditions, and part of the reason I like to write them all in this one list is to just graphically emphasize that they are not the same. Right? If you want to know if a function is differentiable, if this is what you're interested in, don't just check that the partial derivatives exist. Not good enough. Not at all. Right? It's 3 notches down on the list of regularities. Right? So it's important to get this idea that differentiability is a more powerful, more significant concept than just you can take the partial derivatives. And the deceptive thing about this is that in single variable calculus, how do you check in single variable calculus if a function's differentiable? You take the derivative, see if it exists. If it exists, great, differentiable. And it's just more complicated than that here. I also like to point out, I think this is a fun observation, the difference between these 2 very different ideas of partial differentiable and continuously differentiable. The difference is just the continuity of those partial derivatives. Right? All the partial derivatives exist. It's the same definition except for that continuity. Weird that continuity would make that big of a difference. It does. So on an exam, with this point in mind, if you need to use differentiability of a function, and if you're going to prove that the function is differentiable by making this argument that a continuously differentiable function is differentiable, make sure that you write that down. Right? Make sure that you indicate on the exam paper that don't just compute the partial derivatives. You need to point out these are all continuous! Exclamation point. Something like that, and make a big deal out of it. That's because that continuity is what makes this different from that. Okay, so again, in practice, now there's all these different kinds of regularity conditions. In practice, what you're going to be doing is checking this. Right here, I'll do it like this. You're going to be checking this, and then you're going to be concluding that the function is differentiable, which might be necessary for certain conditions of theorems that we're going to be talking about. And then furthermore, you can then conclude that you can compute directional derivatives with the derivative transformation. Okay, last thing in this section, I'm going to show you one example. There's another example up here. You guys can read this one on your own. That's an easy one. But this one's a weird example. This is an example showing the difference between these 2 conditions. I'm going to show you a function that is directionally differentiable. So all the directional derivatives exist, but it is going to fail to be directionally linear. And it's a kind of a weird example, but it's also kind of a fun example. So here it is. It's this function. You can write it as a rational function, or you can write it in polar coordinates. It's a lot simpler to write it down in polar coordinates. But if you want to generate a picture of this, and feel free to pull up Wolfram Alpha or Mathematica or whatever you prefer to use, MATLAB, whatever, and you can type in a simple little formula here, the rational function. And this is the function that has this really unexpected property. So the easiest way to draw the conclusion is to use this formula. Make a quick observation. There's an observation here about how you can rewrite that. There's just some details. This is a nice exercise in thinking about polar coordinates, so I encourage you to read that. Make sure that you follow through, why you can rewrite the function like this. Now the punchline is that you can compute the directional derivatives with an easy formula. There's an easy computation for the directional derivatives. And this is enough information here to show us that this function is directionally differentiable, but not directional linear. Directionally differentiable is obvious because there they are. There's the directional derivatives. No problem. But it's not directional linear because if you look at certain key vectors, think about the angles that those key vectors point and how sine of 3 theta works. These two directional derivatives are 0. If you have here's our domain, and if the directional derivative in that direction is 0, and if the directional derivative in that direction is 0, 0 that way and a 0 that way, well, every vector, whatever vector, is a linear combination of those two, and therefore the directional, if it's directional linear, all the directional derivatives would have to be 0. But they aren't. That function is 0 sometimes, but it's not 0 always. So there's just no way that this function could possibly be directional linear. It's too weird. And there's a wonderful little picture of this. Now, this is a black and white book, so this is the best that I could get into the book. So this is my attempt to draw a graph, and let me confess, I cheated. I traced this from a computer-generated image. So what we have here, that's the origin. The red dot there is the origin, and we've got a function where there's kind of 3 sort of hills on the sides and then 3 sort of valleys in between. But weirdly, the way this is set up, the ridge line of the hill sort of flows into the bottom of that valley. Can everybody kind of see that? So another way to think about this is that we start off, let's let my elbow be the origin. It goes up, and then it comes down, and then it goes down like that, and then up, and then down, etc. So it's just, as you go around, in some sense, there's 3 ups and 3 downs. And in doing so, because 3 is odd, that up is exactly opposite that down, and so you get straight lines. So this entire surface is made up out of a bunch of straight lines through the origin. Up, down, up, down, up, down. Now, thinking about it that way, it's not hard to see why this function's directionally differentiable, because whatever direction you're looking in that direction, you're looking at a straight line. Take that direction there. That's a nice straight line. The cross-section of this surface in that direction, as a straight line, of course, the directional derivative exists. But it's also got so it's tempting to say that this is a nice function, but it's not. This is a weird and creepy function. There is a nasty, odd, weirdo little corner of some sort at the origin. It's not actually a corner, but something weird is going on there. Does that make sense to everybody? Yeah. Well, I encourage you to take this formula here and type that into Wolfram Alpha or whatever is most convenient for you to in a computer algebra system, and get it to pull up a picture of, and then you can kind of look at it from different angles. It's a very interesting, weird surface. Okay. Right. So moving along. Yeah. So next section. So we talked about the derivative transformation. Right, the whole idea of the derivative transformation is that this is a really powerful way to compute directional derivatives, among other things. Said differently, it's a good way to understand how a function changes. It's a single object that you can compute. And once you know that single object, you can compute as many directional derivatives as you want. Just to apply that linear transformation to however many input velocity vectors you might have. So very powerful idea. And as it is a linear transformation, it is represented by a matrix. And we give a name for the matrix representing the derivative transformation. We call it the Jacobian matrix. We use that notation. So capital J. Then as a subscript, you indicate what function are you writing down the derivative matrix for, and at what point are you evaluating that derivative matrix. So, of course, this is the convenient way to talk about linear transformation. Linear transformations are functions. It takes notation to write them down. It's just really easy to represent linear transformations with a matrix. So here's the big question. We know we're going to want to deal with derivative transformations. Powerful tool. How would I go about computing the matrix that represents it? Said differently, with the understanding that I'm going to do it with convenient notation, how do I compute the derivative transformation? It's a huge question. There's a great answer to this question. This is quite possibly my favorite calculation in the course. Certainly up there. And that is, I'm going to compute that Jacobian matrix. I'm going to compute it one column at a time. Now, we've done this back in Chapter 3 when we were talking about how to multiply matrices, how to add matrices. One column at a time is a convenient way to do it. So let's do that here. Let's compute this Jacobian matrix one column at a time. I'm looking at a particular column. Keep in mind, columns are images of standard basis vectors. That's how the matrix notation came up in the first place. Don't forget that the derivative transformation applied to a standard basis vector, any vector actually, is computing a directional derivative. Right? And directional derivatives, if your velocity is a standard basis vector, are just partial derivatives. So, punchline then, the columns of the Jacobian matrix are just made up of partial derivatives. So we get this formula here. There's your Jacobian matrix, and one at a time, the columns are the partial derivatives of the function in question. And don't forget that the way you compute a partial derivative of a vector-valued function is by taking the partials one component at a time. Let me zoom in on that to make that easier to read. So, a given column of the Jacobian matrix, partial derivative with respect to, let's say, x1 here of a vector-valued function f. Well, you just take the x1 partials. You'll notice these are all x1 partials of the various components of f. And let me do some highlighting to help that become clear. So, x1, so you'll notice I'm taking the x1 partials here, and now it's all of the various different components of f. So f is going to have components f1, f2, f3, etc., through fm. So that's one column at a time, so same thing for the other columns. I think this is a great fact. It's a great result. Keep in mind that what's happened here in the space of one page, we started off wanting to talk about this sophisticated way to understand derivatives of multivariable functions. I wanted to talk about the linear transformation. That's the relationship between input changes and output changes. This is the deepest idea on derivatives we're going to have in the course. And the punchline for, yeah, but how do you compute with it? Compute a bunch of partial derivatives. World's easiest derivative to compute. Right? So there's a big sort of contrast on this page between the power that we can apply this to, and how hard it's going to be to apply it, which is not hard, which is computing easy partial derivatives. Okay. Right. So I do feel it necessary to point out sometimes students get a little too sort of confident in the applications of this matrix. Don't forget that even though partial derivatives are easy to compute, arguably they're a little too easy to compute. If you just start computing partial derivatives, well, in some sense, all you know is partial differentiability, which is not much. You don't get to conclude differentiability or directional linearity or really anything. Right? So the mere fact that those partial derivatives exist and you could then assemble them into this Jacobian matrix like this, the mere fact that they exist and that you can assemble them like this basically means nothing. That's absolutely not the point. You got to check and make sure that those are continuous. Conclude continuous differentiability, and therefore differentiability before this means anything at all. Okay. So don't fall for that trap. It's an easy trap to fall into. There's an exercise at the end of this section where the answer, the punchline, it's one of these, how could this be? Resolve the mystery kinds of exercises, and this is how you resolve the mystery. So, yeah. So something to keep in mind. You've got to make sure that the function is differentiable, and you're going to do that by checking the function's continuously differentiable. Okay, and I see now I'm out of time, so this is a good place to stop, and we'll see y'all tomorrow.